standing next to Starship is perhaps the clearest way to truly grasp its immense size. Someday you and I will have that opportunity. When that moment arrives, just how large will Starship actually be? SpaceX continues to refine Starship with the goal of making it larger, stronger, and more capable with every iteration after the progress made with version 3. Attention is now shifting to the next major milestone, version 4, which comes with new revelations shared by Elon Musk. After years of development, we now find ourselves in 2026 with Starship version 3 taking center stage. This iteration of Starship stands at an extraordinary height of 124.44 m with 72.3 m dedicated to the Super Heavy booster and 52.1 m allocated to the ship itself. Even by modern aerospace standards, this is a staggering figure. Starship version 3 is without question the largest space rocket ever launched. In fact, this distinction is not new. Even during the eras of versions 1 and 2, Starship had already claimed the title of the largest rocket in history. What this means is simple. SpaceX is not competing with others for this record. It is competing with itself repeatedly, surpassing its own achievements. That naturally raises an important question. Is this where it ends? When it comes to SpaceX, the idea of a final limit rarely applies. Once again, the company appears ready to push beyond what was previously considered possible. In a recent post on X responding to a comparison of rocket sizes shared by Tesla owner Silicon Valley, Musk made a striking statement. He said Starship 4 will be another 10% to 20% longer. At first glance, this might sound like a modest increase. In reality, it represents a dramatic leap. Starting from the current height of 124.4 m, a 10% increase brings Starship to approximately 136.84 m. A 20% increase pushes it to roughly 149.28 m, which is just shy of the long-discussed 150 m mark. This is the scale we may be approaching with Starship V4. Because Musk referenced a range rather than a single figure, it strongly suggests that V4 could exist in multiple configurations or variants, each optimized for different mission profiles or performance goals. This idea is not entirely new. V4 was previously revealed during an Elon Musk presentation last year. At that time, V4 was shown with a total height of 142 meters consisting of an 81-meter booster and a 61 m ship. That configuration fits neatly within the 10 to 20% growth range and may represent one of the several possible designs. More recently, Musk's mention of a 20% increase points toward an even larger configuration, one that would exceed the earlier 142-meter design and approach the symbolic 150 milestone that has been referenced repeatedly over the years. So, why does this number matter so much? Beyond the obvious visual impact, 100 m represents the fulfillment of some of the most ambitious ideas in rocket history. One of the most extreme concepts ever proposed was Sea Dragon, a colossal launch vehicle envisioned during the Cold War. SeaGro was designed to stand 150 m tall with a diameter of 23 m and to be launched directly from the ocean. Despite its bold vision, it was never built. Starship, however, appears poised to bring that level of ambition into reality. Its sheer scale not only surpasses the legendary Saturn V, which carried humans to the moon, but also succeeds modern heavy-lift vehicles such as the SLS, New Glenn, and Vulcan. This remains true even as those programs continue to evolve and refine their designs. Yet, size alone does not tell the full story. With size comes power, and in this regard, Starship is already operating in a class of its own. The current generation of Raptor 2 engines enabled Starship to reach a maximum lift-off thrust of approximately 7,590 tons, which equates to about 16.7 million pounds of force. With the improvements introduced in V3, total lift-off thrust has now exceeded 9,200 tons or more than 20 million pounds. That level of power already places Starship far beyond any operational rocket in history. But once again, SpaceX does not appear content to stop there. Looking ahead to V4, last year's updates indicated that total thrust could surpass 10,000 tons, translating to more than 22 million pounds. If Starship continues to rely on a 33-engine booster configuration, achieving this level of thrust would require a new engine variant, commonly referred to as Raptor 4. Musk has previously mentioned the possibility of a Raptor engine capable of producing 330 tons of thrust. If such an engine were deployed across a 33-engine booster, Starship could achieve a staggering lift-off thrust of approximately 10,890 tons. That figure would represent yet another unprecedented milestone in rocket propulsion. Even this may not represent the upper limit. There has been ongoing discussion about increasing the number of engines on the booster potentially to 35, 39, or even more. Each additional engine would further amplify Starship's already immense power, making its future performance increasingly difficult to predict. However, Starship's evolution is not solely about becoming larger and more powerful. Equally important is the push to make it better, particularly in terms of reliability, efficiency, and overall quality. A clear improvement trend can be observed when comparing V3 to V2. Reliability has become a central focus. One notable example is the redesign of the booster hot staging system. In V3, this system has been made longer and simpler with the explicit goal of improving efficiency and operational reliability. This simplification brings additional benefits. By reducing mass, the hot staging hardware no longer needs to be jettisoned prior to landing. This change moves Starship closer to true full reusability, which remains one of SpaceX's core objectives. The same philosophy of simplification is evident in engine development. Raptor 3 represents a significant departure from earlier designs. It is lighter, less complex, and easier to manufacture, all while improving reliability. Reducing complexity is especially critical for a vehicle intended to fly frequently as it directly impacts maintenance, turnaround time, and long-term operational stability. This approach extends across many other subsystems as well. Numerous design elements have been streamlined, reducing the number of components and failure points while improving overall robustness. Additional upgrades across both stages have further enhanced performance. One grid fin has been removed while the remaining fins have been enlarged and repositioned. These fins now incorporate additional catching points supporting SpaceX's unique recovery approach. Together, these changes improve aerodynamic control, deceleration, and landing precision. Fuel delivery systems have also received attention. The fuel transfer tube has been increased in size, allowing for more efficient propellant flow to the engines. This improvement supports smoother flip maneuvers during landing and enables more reliable engine restarts, both of which are critical for safe recovery. Another area of improvement involves the composite overwrapped pressure vessels, commonly known as COPVS. These components were heavily criticized following issues encountered during V2 testing. In the updated configuration, the COPVS appear significantly more durable and reliable, addressing one of the key concerns raised during earlier flights. The ship itself has not been overlooked. Perhaps the most critical upgrade on the ship is the heat shield. This system functions as a protective armor, shielding the vehicle from the extreme heat and mechanical stress experienced during atmospheric re-entry and landing. During V2, the heat shield exhibited several issues, including fuel leaks and oxidation. V3 introduced substantial improvements to the heat shield system, addressing these weaknesses and improving its overall durability. Given the importance of safe re-entry for reusability, this upgrade represents a major step forward. Beyond the heat shield, a wide range of refinements have been applied across the ship's structure, systems, and internal layout. Many are subtle and not immediately visible, yet together they drive meaningful gains in performance and reliability. Through 2026, these upgrades will be proven through testing and flight, forming the basis for stable, repeatable operations and establishing Starship as the backbone of SpaceX's future launch architecture. More significantly, these changes lay the groundwork for Starship V4. This next iteration is expected to bring sweeping upgrades across nearly every major system, not simply in size or thrust, but in efficiency, reliability, manufacturability, and operational maturity. Many of these improvements are inherently complex, and their full impact will only emerge once V4 enters active testing. As Starship's capabilities continue to take shape, the broader objective comes into focus. Given its unprecedented scale, the primary aim is payload capacity. Starship V4 is designed to exceed 200 tons to orbit, a long-standing goal for SpaceX. While V3 may approach this threshold, it's unlikely to fully achieve it. V4, by contrast, is being built with that benchmark as a central design target. So, what does a 200-ton payload actually represent? In last year's update, Musk outlined SpaceX's roadmap for Mars settlement. Each launch window would require 10 Starship flights, each delivering 200 tons, placing 1 million tons into low Earth orbit. Of that mass, roughly 250,000 tons would reach the Martian surface. Repeated across for transfer windows, the result is 1 million tons on Mars, enough to build and sustain a city for 1 million people. The entire vision rests on a single requirement. Starship must reliably deliver 200 tons per flight. Without it, the plan slows, fragments, and loses practicality. Unlike the brief expeditions of the last century, future exploration demands permanence. Humanity will not arrive, explore, and depart. It will remain. Building lasting infrastructure with conventional launch vehicles would be painfully slow and labor-intensive. Starship appends that equation as its scale allows massive structures and equipment to be delivered in single launches, compressing construction timelines and simplifying logistics in ways no other vehicle can match. Its design further extends that advantage. Launched vertically, it can settle horizontally and become part of the base itself. Power reinforces these strengths. Higher thrust enables faster transit times, reducing crew exposure to radiation and microgravity while supporting heavier payloads. Equally critical is reliability. As SpaceX prioritizes efficiency and operational stability, a proven Starship becomes the natural platform for long-duration missions where safety is non-negotiable. These technical goals now intersect with geopolitics. Domestically, scrutiny around Artemis 3 is intensifying and progress must accelerate. Success would clearly separate Starship from landers rooted in traditional design. Built for demonstrations rather than sustained exploration. Internationally, competition with China looms large. In the race to establish permanent lunar and Martian footholds, a fully operational Starship offers a decisive advantage. One that sheer scale and performance could place beyond imitation. This brings us to the final question. When will this next giant appear? Last year's roadmap aligned V1 with 2023 to 2024, V2 with 2025, and V3 with 2025 through 2026, with V3 once expected to fly in late 2025. That milestone now appears more likely in 2026 or possibly early 2027, though the broader projections have held up well. Version 4 remains unscheduled, but if V3 defines 2026, a 2027 debut for V4 is plausible, a timeline Musk has referenced repeatedly. If V3 establishes Starship's core capabilities, V4 marks the shift to sustained operational maturity. That moment may align with Artemis 3's planned return of humans to the Moon and potentially SpaceX's first uncrewed mission to Mars. Should that convergence occur, Starship would decisively eclipse every domestic and international competitor. History may be poised to repeat itself. Last century, Saturn V carried humanity to the Moon as the most powerful rocket ever built. In this one, another may soon claim that mantle, not only to return us to the lunar surface, but to stay. We are living at the threshold of that era. All that remains is to watch it unfold.